So we've seen type 1 and type 2 errors and how potent and powerful they can be for real-life situations. So now it's time for us to determine whether we're seeing a type 1 error, a type 2 error, or the correct decision for a few different scenarios. And this will be really helpful if you have that table from the previous page. I'm going to kind of put it right here so we can keep using it. Okay, so if we look at the first one, we want to see that a test is made of the null hypothesis, which is that sigma equals 0.5 ppm, and then the alternative is that sigma is greater than 0.5 ppm. Now you find out that the true value of sigma is 0.6. Now think about this. The true value, which means real life, sigma is 0.6. That would mean, all right, 0.6 is not 0.5. 0.6 is greater than 0.5. So this means that H1 is true. All right, now if we look at our table, if H1 is true, that means we're over here on the right half. Because if H1 is true, H0 is false, and that means I'm either making a type 2 error or a correct decision. All right, so now let's look at the decision that was made. We decided to reject HO. So if you reject HO right here, but H1 was true, that means you made a correct decision. So this is a correct decision. Yay. And I don't want to make it seem like type 1 and type 2 errors are happening all the time. Hypothetically, they're both very low percentages. Correct decisions are where the vast majority of decisions are, hopefully, but these other errors can happen. All right, so now let's look at this one. A test is made of the null hypothesis, HO, which is that mu equals 454 grams, G, and the H1 is mu equals 454 grams. The true value is 454. Okay, so now if the true value is 454, that's real life, but that's 454 right here. That's the null hypothesis. So that means H0 is true. Okay, so if H0 is true, that means we're on the left side. H0 is true here in reality. And then we have to look and see the decision that was made. If we rejected H0, but it was true, that is a type 1 error. That's right here. H0 was true, but we rejected it. So type 1 error. All right, last one. A test is made of H0, which is P equals 20% versus P is less than 20% for the alternative. So the true value is 0.17. Now, 0.17 is less than 20%. So this means that H1 is true. Again, we're on the right half side because H1 in reality is true. So then we have to look at the decision. We chose to not reject the null hypothesis. So if H1 is true, but we do not reject the null hypothesis, that means that we're making a type 2 error right here. Okay, so type 2 error. And they always use Roman numerals. You could use, the regular 1 and 2, but we use Roman numerals. All right, so now that brings us to this very important definitions box. Super important. We're going to use this a lot. Alpha, which is the alpha that we have known for a couple chapters now. We've seen this symbol. Alpha is the probability of making a type 1 error. It's the probability of rejecting the null hypothesis when it is true. This is a definition that is very important. It's a Greek letter, alpha. It's also called the level of significance. So alpha is the level of significance. It's the probability of a type 1 error. It's the probability of rejecting H0 even though it was true. That's what I wrote right here. Now, in general, I'm going to give you alpha. Alpha is not something you can figure out for yourself. We were just going to establish what level of alpha we want for every particular problem we're working on. All right, now, then there is the Greek letter beta. Beta is an important definition, not as important as alpha for us, but very important as well. It's the probability of a type 2 error. It's the probability of not rejecting right? Beta is right here. It's the probability of making this mistake right here. Now remember, both of these mistakes should be low. So the alpha and the beta should be low values, right? Vast majority of the answers will be in the two correct bins, but nevertheless, right? The probability of making that type 2 error. So that's a Greek B, it's beta is how you pronounce it, like the fish, beta fish that they sell in the stores, all right? And then beta is much, much more difficult to deal with than alpha. So we're not actually going to be working with it that much, other than to note this definition right here. The power of a test is called 1 minus beta. It's the probability of rejecting the null hypothesis if the alternative is true. If you're interested in that, if some course at some point wants you to know more about power, you can look up section 10.6 of the text and find out more. Now, for our purposes, we want to think about alpha and beta in a relationship. What kind of relationship do they have? Well, they have an inverse relationship. So that's the first thing to note. Alpha and beta, so here's alpha, here's beta, have an inverse relationship. And I think the easiest way to see this is actually, or the theory of why this is happening is actually to look at our innocent and guilty example. If you decide, hey, I don't want to let an innocent person be wrongfully convicted. I never, never, never want this to happen. What that means is you're going to not convict a lot of people, right? You're going to let a lot of people go, which means automatically this guy's going to go up. Some guilty people are going to get let go and get wrongfully set free. Or vice versa. If you decide, no, 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 no criminals ever on the street, no, 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 put everybody away, then that means that you're going to put away innocent people too, and then this one will go up. So if you want to lower the chance of letting a guilty person go free, if you make this go down, this would be beta, then this would go up. That'd be alpha. So that's the teeter-totter relationship. That's an inverse relationship. If alpha goes down, if you try to lower that alpha, then your beta will go up. Or maybe I should make those the same color here. If this goes down, then this goes up. They go together, right? Like on a teeter-totter. Or if alpha goes up, right? If you want to raise your chances of, well, you wouldn't really want to do that. If you want to lower your chances of ever letting a criminal go free, you're going to raise your chances of putting away innocent people. All right, well, both of these are terrible, right? So why can't we just make them 0? That's this question right here. So alpha and beta cannot be 0, neither one of them, because that would imply that we were 100% certain. And that's impossible. Also, if you lower your alpha to 0, you're going to be raising your beta way up. And that's not good either. Okay. All right. So 2 important things about alpha and beta, and also the definition, which is very important. Right? Alpha is the chance of a type 1 error. So when you have your alpha for particular problems in chapter 10, you have your chance of a type 1 error because they are one and the same. For example, Charlie's going to perform a hypothesis test at the alpha equals 0.05 level of significance. That means that's Charlie's chance of a type 1 error. Felice is going to do the same test at a 0.01 level of significance. So that's her chance of a type 1 error. So if H0 is true, who has the greater chance of making a type 1 error? Well, that's really easy. That's Charlie, right? Charlie, right? The probability of a type 1 error for Charlie is 0.05. That's what alpha is, right? And the probability of a type 1 error for Felice is 0.01 and 0.05 is bigger, which is what they were asking, right? Who has the greater chance, right? Who has the bigger chance of making a type 1 error? It's Charlie, right? That's the bigger number. All right, if H naught is false, who has the greater probability of making a type 2 error? That's trickier, right? Because a type 2 error is beta. Now, beta goes up when alpha goes down, right? So let's remember, type 2 error, the probability of a type 2 error is beta. So what I'm really asking is, who has the higher beta? Well, I didn't give you beta. I gave you alphas. But alpha and beta have an inverse relationship. So the higher beta would go with, so who has a higher beta? The person with the lower alpha. And that would be Felice, right? Felice has the lower alpha. And since her alpha is lower, that means her beta will be higher. Because, of course, alpha and beta have an inverse relationship. When you raise your beta, you lower your alpha. Lowest alpha gets you highest beta. And that's Felice in this instance.